Alright, hell yeah. So we have problems in physics, we got Krotov, and we got problem 1.3, you know what I mean? And man, this is the second video on it. I'm just going to quickly go through it because these problems are worded so weirdly that it's just like, I don't know what the hell they're even talking about until I try to solve it one way and then realize, nah, I'm not even solving it the way they want it to be solved. So we have a helicopter, and it starts at time 0, and then it goes up into the air. It says it travels along the vertical with an acceleration of 3 meters per second. To me, that means it's going straight up into the air. But then I said, if it's going up in the air for about 30 seconds, it's going to go about 130 miles an hour. And I just don't think a helicopter can travel vertically up at that speed. I mean, this problem makes sense if this said horizontal. It takes off and then goes horizontally with an acceleration. That's the only... Helicopters can go 180 miles an hour in the horizontal. That's for sure. But vertical, no, that doesn't make any sense. But it doesn't matter anyway. You know what I mean? Whether you're going horizontally or vertically, you're still getting hella far away with an acceleration of 3 meters per second. And so the equations that we use from the integration approach is cool. 3, integrate that, becomes, we have a velocity equation that's 3t. Then we get a position equation that's 1.5t squared. Okay, hell yeah. And now we need a continuity that says, well, hey, this thing's going to go, and the problem says is like when it goes up in the air, at time 0 you start a stopwatch, and you hear that the engine shuts off at 30 seconds. Well, what happens theoretically, I mean in reality, is at 26 seconds, the engine shuts off, but this helicopter is hella high, or like really far away, and it just takes over 3 seconds for that sound to get to you of the engine shutting off. So, you know what I mean? So when you heard the engine shut off at 30 seconds with your stopwatch, it actually happened at 26. Cool. So then we have, you have to figure out, well, that time. So we just call it a variable, and we say, hey, time at time ta, this is going to be that like 26, plus the time that it takes for that sound to travel to you, that's going to be equal to 30 seconds. So there's our continuity equation right there. And so then what else happens? How do we find the time for that sound to get to you? Well, we need to know how far we are away. And if we're 320 meters away, it's going to take 1 second. But we're actually hella high after we do this thing. And we go over that in the video. But you take this height, and this is our equation for height, 1.5 ta squared. And then you divide that by 320. So that's what I have right here. The time for the sound to get to you is that height divided by the velocity of sound. Cool. So now let's look at this equation, because we have the time for sound and then the time, you know, for acceleration. And so we have this as our continuity, so we can solve for the we can rearrange this for the time for the sound is 30 minus the 26 time for acceleration. Throw that into this side of the equation. That's what we did. And then just get everything on one side equals to 0, and we're going to have a x squared plus x plus a, we're basically going to have a quadratic. So then this is my a term, this is 1 is my b term, and negative 30 is my c term. Here's the quadratic. That's all I did. And now you get that time for acceleration. It's just 26.6. And then at the end of this video, it wasn't until actually going back and be like, well, what do they actually want? Determine the velocity of the helicopter at the moment the engine actually switches off. So I derived a couple other equations because I wanted to know, like, hey, like where that helicopter was, after the sound gets to me. Like after the sound actually gets to me at 30 seconds, what's the speed of it? But no, they still just want to use these equations. So all we have to do is take this equation, and then we're going to do VTA. We already solved for TA, and so that's what we did right here. So we have 3 times 26.6, and heck yeah, we get a velocity of 80 meters per second. Final answer. And finally, heck yeah, I'm done with this one. And you can watch the whole video because we learn a ton in how to make equations. You know what I mean? Like, hey, using the numbers, throw the numbers at it, and try to get an equation for the problem. All right, so sit back and relax and enjoy. All right, hell yeah. So these problems are out of the problems of physics. This is the aptitude test. This is the author is Krotov or whatever. Anyway, so this is problem 1.3. We've done this one, you know, and we did it just by throwing numbers at it. So now this video is like, how do you get an equation for something? You know what I mean? So this is a helicopter. It takes off, accelerates. Change in velocity for every second is 3 meters per second. That's the definition of acceleration. Change in velocity, change in time. That's going to be a change in velocity of 3 meters per second every 1 second. Cool. And when this helicopter takes off, 30 seconds later, you know what I mean, a time, you know, of, I don't know, just 30 seconds later, you on the ground, and this helicopter goes straight up, you on the ground hear that the engine cuts out. Well, guess what? The engine cuts out actually maybe 2 to 3 seconds earlier because it's way the hell up high, and if it's even 320 meters off the ground, it takes sound 320 meters, you know, it'll travel that distance in 1 second. That's what this equation, the velocity of speed of sound. And we found out that the helicopter's more than 3 times that height, and then shuts off its engine, and it takes more than 3 seconds for that sound to get to your ear. And we'll do it once just because I just did it by guess and check, and I found that, hey, 26.75 seconds of you know, from the second it takes off the ground and just to guess when it shuts off its engine. Well, if that's the case, 26.75 times 3 meters per second, this thing at this height is going to go 80.25 meters per second. See what we did there? This is the acceleration, and for every second that engine is on, it's going to increase in velocity by 3 meters per second every second. And you got 26.7 seconds to do that. Velocity on the ground is 0, obviously. And so then what we use is like, well, it's not like we were going 80 miles per hour the entire, meters per second the entire time. So you need to get the average velocity, which in this case, it's real easy. It's just the max velocity divided by 2. And so we divide that by 2, we get something like 40.125 meters per second. And if we travel this average velocity for that time, and we multiply those two things again, and don't you remember, we just multiplied something by this 26.75. We multiplied by the acceleration to get this max velocity, then we divided by 2, we got the average velocity, and guess what? We're going to multiply by the seconds again, 26.75. And we get this final height, or no, we get the height of the engine shutting off of 1,073 meters. Cool. But then it takes a few seconds for that sound to travel to our ear, and it's because 320 meters per second, seconds cancel, so we're gonna divide by that basically, and meters are gonna cancel, seconds pops to the top. That's what I meant to say. So I'm gonna store this as alpha d for our distance, and we can store this as alpha v for our velocity, and then so yeah, let's take this distance divided by 320. I'm going to store this as alpha t. So this is going to be the time at 3.35 seconds for that sound to get to our ear. And it asks, once that sound gets to our ear, or basically it says the sound dies away from the engine, we want to know the velocity of the helicopter at that immediate time that the sound dies away. And we're saying that's 30 seconds. And let's see if we have a check on reality, because this time that we found, alpha t, plus our original time of 26.75, is very close to that 30 seconds. You know what I mean? We're kind of overestimating, so that this needs to come down just a little bit. Cool. And so what happens to the helicopter in that 3 seconds? Well, it has no engine. And for this problem to make any sort of sense, the engine just has to cut off instantaneously. And then it's just got upward velocity, but it's got a hell of a lot of upward velocity. So it'd be the same thing as like throwing a rock, or like shooting projectile from the earth, or throwing something up with an initial velocity of 80.25. If you're throwing it straight up, 80.25 meters per second, what's going to happen in 3 seconds? Well, actually, it's just going to slow down. Gravity is acting on it. And what is gravity? Gravity, and for me, I'm just going to say gravity is 10 meters per second squared. And what does that mean for gravity? That means we're going to have a change in velocity of 10 meters per second every 1 second. You know what I mean? Hey, it's an acceleration term. So we're going to have 3 seconds between that engine cutting and us hearing it. So it's just like that helicopter is a projectile going straight up, but now losing 10 meters per second of velocity every second. And it's 3.35. So the equation there is 80.25, that original velocity, minus the acceleration of gravity, 10 meters per second squared, times time, which will be 3.35. Cool. So that's going to be AD, that initial velocity, minus 10 times alpha t. And we get a final velocity, that's the equation, I mean that's the problem, but of approximately 46.7 meters per second. So that's the problem in a nutshell. Now see how we did a bunch of things? We found a time, and then we multiplied by acceleration, we divided by 2, and then we multiplied by time again to get distance. We took that distance and divided by the speed of sound to find a time value, and this time value was due to a projectile going up in the air, but gravity is acting on it, in the opposite direction, slowing it down. You know what I mean? 10 meters per second every one of those seconds. And then we're going to have a final velocity. It could have said what was the height from when the engine kills to the 3.35 seconds later, but it doesn't. It just says what's the final velocity. Okay, so now, like, I find if you pay attention to what you did, it can be easier to at least have a double check, on your equations to make sure they make sense. But I don't know, like, I'm just gonna go through this one like I would solve it. I think getting numbers on it and doing it like I just did, like the guess and check model, is kind of totally different than the equation model. Okay, so let's see the equation model. The equation model says we start with acceleration is 3 meters per second squared. We know that acceleration is change in velocity, change in time. You can also write this dv dt. So this is the integration approach. So cool. Acceleration is equal to dv dt. So now we're just going to write dv dt in place of this acceleration. That's all we did. And then we have 3 meters per second squared. Now we separate variables, and we get dv is equal to 3 dt. You know what I mean? I'm dropping the units because we're just good to go. But even right here, you're just like, what are we integrating? You know what I mean? So what I like to do is change even this acceleration equation that says 3 meters per second squared. Well, we can say acceleration is 3 times t to the 0 meters per second squared. It's a function of time, but to the 0 power. So it's kind of a function of time, it's kind of not, because this means that at any time, like when this helicopter is traveling up at time 10 seconds, what's its acceleration? So we throw in 3 10 seconds to the 0 power, and guess what? 10 to the 0 is just 1, so we get 3 to the 1, and then we just get 3 meters per second. It's the same number, you know what I mean? And so, all right, hell yeah. So, and now we'll just kind of get to it. So this, when we integrate we get an equation for velocity as a function of time. And when we integrate this, it goes to 3. And this was, well, we can go back to this. Integration of 3 to the t to the 0 dt. Well, cool. Integrating it, you can pop out the constant if you want, and you can do 3 integration of t to the 0 dt. But when we integrate t to the 0, basically integration method, just, the simplest way is just t to the 0 plus 1 divided by 0 plus 1. Because I find it complex when you're just integrating constants. I think mentally it's just like, what are we integrating? You know what I mean? It's really simple when you got like integration of t squared. You're like, oh, hell yeah, I know what to do. I'm gonna do this t cubed, and then what do I have to do? 1/3. We kind of know those integration rules. But the integration rules still apply here, and then plus a constant. So this becomes t to the 1 divided by 1. So cool, it's just t to the 1, and then the constant. The constant comes in because this is an equation for velocity, and we have to make sure it checks on reality. So when we throw in time is equal to 0, helicopter is on the ground, velocity is 0. So you can write that like this. Either time is equal to 0, velocity is equal to 0, and then our equation 3 to the 0 to the 1 power plus c. So now we have 3 is equal to, this becomes 0, 0 plus c, c is equal to 0. I mean, that's just 4 steps to just, state the obvious. Okay, but now we do the same thing. This is the equation for acceleration. Same thing with velocity. What is velocity? Well, it's the change in position, change in time. It's dx dt. So we can do that same thing with this velocity equation. We can put dx dt is equal to this equation, 3t, and I'll still keep this 1 here, and then that's it. And then separate variables, we get dx is equal to 3t to the 1 dt, sorry about that. And then when we integrate, we get an equation that says x as a function of t is equal to 3t to the 1 plus 1 divided by 1 plus 1, plus a constant. So we simplify this just by saying, hey, this is 3 divided by 2, so cool. So we get, I'm just going to say 1.5 t squared, and then this one. At time is equal to 0, what's our position? Well, let's just say position down here is 0. I mean, you can put this position anywhere. That's the interesting thing about setting a datum on position. But ground, 0, that makes sense to me. Cool, so now we have position. I mean, you could set this as the altitude. Let's say we're just at 5,000, feet. Let's say we're just at 1,000 meters above sea level. You could set that as your datum, you know what I mean? But yeah, we're just going to set that as equal to 0. So cool, now we have an equation. We got an equation for velocity, and we got an equation for position. And so this will say, but now, since we already did the problem, we know that this acceleration isn't going to be 30 seconds. Because if this helicopter accelerates for 30 seconds and then cuts its engine off, and we have a stopwatch on the ground, and we measure that same 30 seconds and we hear the engine shut off, that means that sound got to our ear instantaneously. It can't happen that way. So this helicopter has to shut off its engine a few seconds lower than 30. So we at least know that. So cool. And then, and in my previous videos, like, hey, we have some huge checks on reality with any equation. Because even this equation that says velocity is a function of time, well, it's because this helicopter is accelerating. But we know, a helicopter can't just keep accelerating at 3 meters per second as it goes into thinner and thinner air. It just probably can't. It would have to rev higher, and then there's just a physical limit. It can't go into outer space. So theoretically, it can't go this acceleration for forever. And I even thought 30 seconds. I haven't looked that one up online, but going 80, that's 80 times 2.23. That's 180 miles per hour straight up. And unless I just have this problem way off base, I was like, well, wouldn't it make sense if the helicopter was going horizontal? You know what I mean? Accelerating horizontally. And did I read it wrong? A helicopter takes off along the vertical with an acceleration. See, I'm hoping this problem is junk, because, or I hope I'm very impressed with helicopters that you could have an upward speed of 180 miles an hour. I don't think so. But there is a check on reality. You wouldn't be able to, this problem would hella not make sense if you said 60 seconds. I could bet my life on that. It would have to be like a rocket ship that had an engine shut off. And we're just talking helicopters here. Okay, so yeah, so that means that every equation has a check on reality. You know what I mean? And this equation's a function of time. What was it? Yeah, like we said, is time going to be a huge number, infinity? No. And even here, you can't have an increase in velocity past a certain point. All right, cool. And then, but how do you get an equation on these things is you do need a continuity. And I think I've done a couple of these where the time, this 26 seconds is one time parameter, and then the time for the sound to get to you is another time parameter. So I do this TA for time to accelerate, and then once the acceleration is done, we're going to have time for the sound to get to us, and that's going to be equal to 30 seconds. Now, I have not looked this problem up in any books or anything. I just know that these simple continuities are actually the thing that are very difficult to be like, oh, I don't realize that right off the bat. But this now will be very useful to us, and we can even change our velocity equation. We can say velocity for, and I don't know if we should just like have this as a function of t acceleration. You know what I mean? I don't know, that might be too much, but this is going to be 3t acceleration, and then our position as a function of t acceleration is going to be 1.5 t acceleration squared. Cool, so now let's take the problem where we get to this final velocity, and we know it. We know this final velocity, and we kind of know the time to acceleration because we've thrown some numbers at it, but we got to treat it like these are unknowns, and we kind of have to label you know, what they are. So I'm going to say that this is velocity at t equals, you know, at TA. I'm going to say TA is that time that is basically 26.75 seconds. So now you can kind of see that relationship. And I want to know, and the velocity at that time, well, it's just going to be 3t TA. So there you go. I even know the velocity at that time. Because we have to do the same thing. As we did this and integrated with 3 meters per second, we got to do the same thing with gravity being 10 meters per second squared. So let's do that. So we have, let's see if we can do it all in one step. We have acceleration is dv dt. So now you know that acceleration is change in velocity, change in t. I like to do it like this because these values can be substantial. You can take 1 second chunks and then find the change in velocity. That's what we did. And you can take as big a chunk as you want. As long as this is a constant, you can take the whole chunk. I can say, well, what's my time? 26.75. That's a huge change in time chunk. And how did I find the change in velocity? Well, it's because you have you have an equation here. As long as that's a constant, like hell yeah. Like this is an equation with you can lay it out like this. Change in velocity, change in time. You can solve for change in time. Just bring the a downstairs. That's change in velocity a. Or you could solve for change in velocity. And that's going to be a change in t. And that's what we did. We used this equation and said, hey, 3 times 26.75. And hell yeah, that's how we got that max velocity. All right, sweet. So we're going to do that same thing. And yeah. So this part is just it's real easy to see that acceleration is change in velocity for every 1 second of time. But if you do dv dt, this is kind of incremental, and this is kind of where you can get it like this, and then separate variables and integrate. You know what I mean? And so for gravity, I guess we're going to say that gravity is going to be negative. Because we've already said acceleration is positive in this direction. We're increasing in velocity. And so gravity is going to change our velocity by negative 10 meters per second. So if we're at 80, in 1 second we're going to go to 70, then to 60, then to 50. And that's kind of what we find out, 50, 45. Okay, so we have... Alright, hell yeah. So we're on a roll, so we're going to do 10, and then we're going to put the dt up here. We're going to integrate. So we're going to get velocity as a function of time is, I'm sorry, this is negative 10. So it is negative 10 t, and then plus a constant. So now we say, and this is going to be t sound, you know what I mean? Because that's our limit. You know, it's going to take about 3 seconds. So this t value is going to be 0 to like 3.5 seconds. Okay, so and when that time is 0, right at the second the engine shuts off, what's our velocity? Well, we have a positive velocity. So remember how I shouldn't have done this all in one step, but hell yeah. So you separate variables, you get v is equal to negative 10 t plus a constant. So now I say when time is 0, what's my velocity at time 0? You know what I mean? I'm going to say velocity at 0 is equal to negative 10, 0 plus c. Well, now I have, oh, what the hell? Oh, well, I need to know my velocity at time 0. So yes, I know it's 80.25 meters per second. So cool. So this becomes negative 10 plus c is equal to 80. I'm sorry. This was negative 10 times t. So at t equal to 0, this goes to 0, and we see that our constant is just 80.25 meters per second. And this just kind of proves the kinematic equations. Where you know what I mean, if you integrate acceleration, you get the velocity equation as a function of that acceleration plus velocity initial, you know what I mean, which is 80.25. Cool. In our case. And now we're going to set this equal to dx dt, separate variables, and we got negative 10 ts plus 80.25. We'll bring the dt out here and integrate both sides. Now we have an equation for position, and this is going to be negative 10, and this ts, if we integrate it, this is already t to the 1. So take your time and go t to the 1 plus 1 divided by 1 plus 1. And that's going to be t squared divided by 2. So we're going to get negative 5 t squared, and then plus 80.25 t. Because this is t to the 0, we're going to go t to the 0 plus 1 divided by 0 plus 1. Alright, hell yeah. And then even here we have a constant. So at time, this is where you have to go back to this equation, because if this is ts, at time is equal to 0, well, aren't we hella off the ground? And yeah, we are. But we don't know that yet. I mean, we know because we threw in the values of 1,000. But how high are we off the ground? Well, we have to throw in this equation for TA, because we know our time acceleration is 26.75, and when we do that, that's our position. So we have to say when time is equal to 0, and we know our position, it's 1.5 TA squared. And that's why doing this with letters, you might not realize that, oh, this is TS, this is the time, this equation is based on that time for sound to get to us. That's going to be our position, and we're going to go negative. You know, because of that value, pretty much. Well, we're still going to be increasing height. We're still a projectile. Once the engine shuts off, we're still going higher, but we're going slower, and it will hit a point. And if it takes a long time for the sound to get to us, well, we'll stop and then start plummeting back to Earth like a stone. And we just want to know where we are. I think we're like right there on the path. We haven't, you know, stalled out and then came back, because we're already going 80 meters per second, and that sound only takes 3 seconds to get to us. We're going to go from 80 to 70 to 60 to 50 meters per second. You know, we're still going upward. Cool. Okay, but yeah, so that's where doing things by equations is like, well, this might not be so evident. 1.5 TA squared, and I apologize I don't have A on this. I do over here, well, yeah, so here's the two equations I'm using, and then we'll match them up. Okay, so now we have an equation for position, for when the speed of sound gets to us, and then equation for the velocity. So now we still have to kind of go back to that continuity of like, well, how do we, what the hell are we solving for? You know what I mean? Well, we're trying to solve for the velocity, you know, after this, yeah, this equation right here. If we know, so we said this was 30 seconds total. If we did know that this was 26.75, well, this is really easy. We can just do 30 minus 26.75. Find out that this is 3.25. Cool. Throw it into our equation. We're going to have negative 10 times that answer plus 80.25. And hell yeah, we're going to know our velocity is 47.75. But unless you've spent like your whole lifetime working with these equations, I hate the way first year physics is taught, because they're just like, oh yeah, use the kinematic equations. And they don't even teach you how to integrate them. So they just say, you know how like this is negative 5? Where does that come from? Well, that's that gravity divided by 2. Yeah, so position, the kinematic equation for this is 1/2 acceleration t squared plus velocity initial t plus the position initial. I mean, we did that. Integration will give you every step of that. You know what I mean? To memorize this equation is just like, yeah, right. You know what I mean? You would have it in your brain for the first chapter problems, and that's it. And then it's going to be gone for the rest of your life. You're not going to learn it. So using the integration approach, or forget integration and just throw numbers at it and see what you're doing to that. That's where it's at. Okay, so because even right now I'm just at a pause of just like, well, damn it, I don't know what to put together. Oh, but we do have this position. Oh, so now this is our position. I don't think we're even going to use this one. This is the one that I was interested in, because after the engine shuts off, I kind of wanted to know how high we got. You know, that if we had a second question and be like, well, once you heard the engine at 30 seconds shut off, how high is the helicopter at that point? Well, that would be this. We can find that value of, and let's do that right now. And we got the equation, friggin' A. So we got negative 5 times, let's see what we got. So if this is, I guess we'll do it again. 30 minus 26.75. So this is 3.25. We got negative 5 times 3.25 squared plus 80.25 times 3.25 plus 1.5 times 26.75 squared. And if I didn't totally munch that, you know what I mean, we're gonna have a height of 1,281 meters, and that's sweet, because look at that. We were at 1,073. How do we do a check on reality? You know what I mean? We just subtract 10,073. So we go up an extra 208 meters. And what would be our average velocity if we did that in 3.25 seconds? You know what I mean? And this is where you're like, hell yeah, units are the equation. I mean, even for me, I'm doing this right now. Time is 3.25 seconds. So I know the units on that. And what am I? And then distance is in meters, and that's 208. And what am I trying to find? The average velocity during that time? Sure. So it's just meters divided by second. So we're going to do this divided by that 3.25. Our average velocity during that time is 64.1 meters per second. And so so then we know that our actual velocity is, did we even solve for actual velocity? I totally forget. Didn't we say 80.25? Because I think I just made an error here. I don't think so, but we're gonna subtract like 3.25 times gravity 10. So our velocity once at 30 seconds is going to be 47.75. That's what we were thinking. And our average velocity, yeah, it's still hella. It's still halfway between our that velocity. See how 80 80.25, and how do you find the average velocity between these two? You add them and divide by 2. It's like that equation. You can't know. That's just one to always have in your pocketbook. Cool, and then you get that 64. Okay, so sweet. Like, I think we're... Alright, hell yeah. Now, this is so cool because we're just so close, you know what I mean? It's like we can't make a mistake, but it's just, like, for the life of me, man, it's so hard to put these equations together. So what are we trying to find? We're trying to find this velocity when the times, we're just trying to solve this equation once we know TS. But we don't know TS. In this, so this equation we don't know TS. This equation we would know TS if we knew TA. So then we need to have a place where those two equations are the same. And isn't it this where now. Even though this is bizarre, because even though this right here is the initial X position when the engine shuts off, this equation is solely a function of this time. Like, this is a constant, you know what I mean? This is your initial position, so that's why this equation is tripping me out, because the continuity is that these two are equal. It says well, no. It says this at TS is equal to 0. We already did that. You know, you throw in this is equal to 0. It is equal to that, and so that we already did that. I feel. Oh yeah, no duh. So then you actually. You solve for TS. You have a quadratic, and then you can solve for TS. Is that right? Is that how that works out? Holy Toledo. What? I mean, if you say these are 0, then oh man, this is such a bummer. Yeah. I mean, this is where I'm just racking my. This is the issue that I get into all the time. Is just like I don't see the continuity, and I'm gonna turn off the camera because I swear, if I can just take like 1 minute, it helps me so much. Hell yeah, and that took about 15 seconds. Actually, about 30. I'll be honest, but no. Yeah, is like this equate like these simple continuity equations is just like that's the gold. Because, and then if you get this stupid continuity equation, you can also, you know what I mean, just start writing this 3 times. So we have TA plus TS, and honestly, I don't like, you know, it's so hard to have a variable on time that's enjoyable. You know, maybe T and T prime, I don't know. But I think we're doing a good job here. I think that's pretty easy. And then is equal to 30. So this also says that TA is equal to 30 minus TS. Or you could say TS is equal to 30 minus TA. So hell yeah. And so now we can start using those equations. We can throw. Oh shoot! I thought I had it, but. What I was going to do was throw in, I was going to change this TA. Hey, we have, oh, this is hilarious. You know what I mean? I totally forgot. So we're going to throw some more mental power at this. Because I totally forgot what the hell TS was, you know. And the fact that TS is a function of the height that we get to. Yeah, so that's this equation. So once we get up to this height, holy Toledo, you know what I mean? So when we do throw TA into this equation, we're going to be at that height, at x is equal to TA. That's going to give us that value of that height. Once we know the value of that height, what did we do? Well, we said that was like 1,000 meters. So then we took that and we divided by 300. Yeah, then we divided by 320 to get TS. So there's an equation. It says x evaluated at TA divided by the speed of sound, and I'm just going to say VS, velocity of sound, that is the definition of TS. So cool. So there you go. And so, you know, now anywhere where we have TS, we can throw in this into that. All right, sweet. And don't we have TS right there? You know what I mean? Wouldn't that be the place to do it? Shoot. Yeah, it's so interesting how like I can do the answer just using the numbers, but then finding the equation, man, it's difficult. Okay, so, but even here, I do not know what TA is. I know it's less than 30 because it's got to be 30 minus TS. Oh, perfect. Now we're on a roll. So it spelled itself out. So let's write down this equation for x of TA. And sometimes writing these equations like this doesn't really help to see what they are and how they're useful. Is this squared? 1.5 TA squared. Sure it is. Okay, and now we have this continuity equation that once we get x of TA, we're going to divide by the speed of sound, and that's going to equal TS. Cool, but I already know that we have this continuity that says, hey, this TA is 30 minus TS. So heck yeah. So even right here, do we have enough things to solve? I'm going to put this into that equation, and it's going to be right there. That's all this is going to be. We're going to have TA squared divided by a constant, that's the speed of sound, is equal to TS. I have one equation, two unknowns. Can't solve it. But then I have another equation over here that says, hey, I can throw in this TA, I can throw in this value right into there, and then I'll have, and that'll be sweet. And that's what I want to solve. If I solve for TS, then I can come back and throw it into this equation, and I can get my velocity as a function, you know, evaluated at TS is negative 10 TS plus 80.25. All right, heck yeah. Now that's where, if I wanted to do this thing, you know, just with better variables, I would have said this equation would be just V of T prime at negative T plus 80.25. I'm sorry, T prime at 80. You know, but even the prime's weird because it looks like it's T to the 1. And then I would say, you know, my other equations for this x, I would say this x is just a function of t. So I would say TA is just t, and then t, and it's not, how I have it written is, I guess I wouldn't do this way again because it's confusing. Because this TA term, what I'm saying, is the function. This can be 0 to the time of acceleration, max, which is like 26.5. So just having this equation written as 1.5 t squared, I think this is better visual. I can say, sure, the max time here of acceleration is TA. So I can say when t is equal to TA, that's going to be when the engine shuts off. And then for this equation, I can say when t prime is equal to ts, that's the time that it takes for that sound to, that's the last bit, when the engine shuts off, the last bit of sound wave that was created is finally hitting my ear, and there's no more sound, traveling to my ear. So that's a better explanation. Okay, so sweet. So now we can just plug and chug. How should we do this? Well, at least we have our equation here. Get a better pen. So we're going to have 1.5 TA squared divided by that speed of sound. That's a constant. And even just writing this VS, I don't like that at all. I think C is the speed of light. Speed of sound, I don't know what kind of variable you would put on it. I don't know, just C prime. But anyway. And that's going to equal TS. Okay, so now we're going to have TA squared. We know TA is this. So what's 30 minus TS squared? Finally, some math that I just like. You know, this is the way I square. I FOIL it, I do this. Hey, just 30, we're going to square that one. So it's 30 times 30, that's 900. Cool. And we're going to square that one. Let's do it. And it's always going to be a positive. So it's just TS squared. Okay, now you do that, you know, thing where you multiply these two together. So we're going to have a negative, and we're going to have a, you know, 30 times TS. But there's two of them, because we're going to do, that's the only thing you have to remember. There's two of them. So we're going to do 60 TS. Cool. So that's our equation right there. And now it looks like we're going to divide by the speed of sound, and that's going to equal TS. So now we have to maybe distribute this through, and let's distribute this through and then bring this over. So and let's get this out front. So we're going to have 1 divided by VS TS squared. So that's this term. Now we're going to have minus, I'm just going to do this in one step because I want to get on with life. We're going to have minus parentheses 60. Oh, bummer. Maybe I shouldn't do this in one step. This is going to be 60 divided by VS, and then times TS. Now I can subtract this TS, and then now we have plus 900 is equal to, I did that garbage. I apologize. I just really wanted to combine these two terms because we have a quadratic. And that was the most interesting part to me. I really wanted to get to the quadratic fairly simply. So now this term right here, ooh, this is ugly. But oh, I hate negatives. So we have negative, because how do you factor it out? I want to factor out a TS. So let's do that first. So we're going to break out a TS. And now we're just going to say we got negative 60 VS minus 1. Oof, yeah, see. And I can have a plus sign here. Or I can have a negative sign out here and then change these to pluses. Is that how it is? Because I could foil, if I have a negative outside, I have to foil it through or something. Holy Toledo. Or I could just leave it like that and not run. Well, yeah, let's do it. So we're just going to have negative TS is equal to 60 divided by VS plus 1. All right, let's write this over here. So we're going to have 1 divided by VS TS squared minus TS. We're going to have 60 divided by VS minus 1. Cool. And now you're going to have plus 900 is equal to 0. Hell yeah. So now we can actually do, we're doing this one. We're doing it. Cool. So now, you know, it's just, I don't like when equations kind of just feel a little bit dirty. You know what I mean? You're just like, oh, damn it. Because it feels like you made a mistake, or it's just going to be much harder than it needs to be. But we have the quadratic here. And, yeah, we're already deep into this video. So we're going to solve the quadratic. So we have something like AT squared plus BT plus C is equal to 0. You know what I mean? Hey, we have, that was really hard to say. AX squared plus BX plus C is equal to 0. That's what we have. And we got to write it kind of like this. So we're going to go, put the constants in parentheses. Cool. So we're going to have that TS squared. And then minus, whoa. And then from here on out, we're changing this to x. You know what I mean? Sometimes I like to do that, and it makes my brain take a vacation. So we're going to go x squared. And then right here, I don't mind the negative, but let's get that. And what the hell? I'm just making mistakes, man. And, you know, could I prove it? Could I prove that negative 5 minus 1 is negative 6 is the same thing as negative 5 plus 1. You know what I mean? Sometimes you just have to do the dumbest numbers in there just to be like, am I just foiling a negative through? This should be the simplest thing, I swear. Okay, and then so we're going to just bring out this constant out front. And so we're going to have 60 VS. I don't like that VS. C prime would not. We have too many C's. I hate when there's like not enough symbols in the known universe just to have different symbols so they just don't look all the same. Okay, so now we have X plus 900. Okay, hell yeah. So now we have our A term. We have our B term, and our B term is negative. So you really have to focus on that to not make mistakes. And we could just say x is negative b plus or minus the square root of b squared minus 4ac all divided by 2a. And how do I memorize that? Well, I know that it's a negative b because the equation sucks. You know what I mean? The negatives suck. Oh, and you're just going to make hella mistakes in this. That's the first part of this equation. You can just know quadratic sucks. So it must have a negative and a negative b. I think we can all remember that. And then you have a square root plus or minus. Yeah, we get it. We get it. That's where the plus or minus is. And then underneath the square root, well, you have to have squared terms. You know what I mean? Well, we're taking x squared, we're taking b squared, squaring it, and, you're getting a b term. Because, sorry, the smoke is just crazy. But anyway, and I might need to get some water, too. But yeah, you'll have a b squared under the square root. So once you square, it's just a b. So yeah, so that's when you know you got a b squared. And hell no, there's not a negative b squared. You know what I mean? That would be make this thing insane. You know, but your negative is right here because the other part of this is like, hey, it has to have a negative because if it was just positive, this would always be a positive number. But we do have a negative there because one of the answers sucks. It's an imaginary. And then just all divided by 2a. I guess you could make a mistake and not all divided, but I think that's the only part that people know. It's like, hey, all divided by 2a. That's like the only part people know. Okay, so what we're going to do is this is how I quickly derive it. This a, you got to get rid of it. You have to get this in terms of x squared plus blah, blah, blah. So all we have to do is divide everything by a. So cool, that's the first step. X squared plus ba x plus ca is equal to 0. Alright, now let's get that the hell over there. So you're going to have x squared plus bax is equal to negative ca. Cool. Alright, so now we're just going to square these. You know what I mean? So, basically we're going to get something like this. We're going to get x, and I guess it's going to be plus. Yeah, keep our life simple. And x plus something times, we're going to square it. Essentially what you're going to get is this. Squared is equal to, something, and then you can take the square root of this. You can take the square root of both sides. Cool, then you're going to have x plus that something, and then you can minus that something. Cool, so that's a little foreshadow of where we're going with this. Okay, so, but how do you get this? Well, we know from what I was doing is like, oh, if you have x squared, the first term is just going to be x squared. Hey, the next term is just going to be those two things squared. So we're going to have that squared. And then the next thing we're going to have is x times that thing. You know what I mean? And we're going to have two of them. And guess what? That is going to be this. So we're going to have, so whatever this is, it has to be that. So we're going to have b divided by a, and then it's just one half of that. I did a horrible job of explaining that, but now we'll just throw it in and you can see why. So we have b over 2a, and we're going to, now we can just square that. So let's use our rules. We're going to have x squared plus b squared 2 squared a squared. That's a bizarre way to do it, or you could just say we have b over 2a everything squared. Okay, and now we're going to have that term where we go x times this. So we're going to have x times b divided by a, but we're going to have, I guess I'll just x times b divided by 2a. But we're going to have two of these. Cool. So the 2's cancel, and you have x divided by ba. Well, isn't that what we have right there? Hell yeah. So we definitely know this jives. But we actually have this other term. I'm doing I need to make a separate video on this, but yeah, you have this term and that term. Those check out, but then you just created this other term, which we don't have right here. We don't have that term right here. You know what I mean? So we're just going to have to add it right there. So we're going to do b over 2a all squared. And then over here we have to add it too. B over 2a all squared. Okay, heck yeah. So now finally this is that. I mean, this is that. So let's do it. So we have x plus b over 2a all squared is equal to negative c divided by a plus b over 2a all squared. So now we can take the square root of this and square root of that, and now we'll get x plus b over 2a is equal to this. Cool. And let's just do it in one step because we'll just have to subtract this b divided by 2a. So we're going to get x is equal to plus or minus the square root negative c divided by a plus b over 2a squared. And then we're going to subtract, I shouldn't have crossed it out, but we're going to subtract, what the hell was this? This was the x plus b divided by 2a. This is the part we squared, so we were able to square it to get to the inside terms. That squared this side of the equation, and now we're going to subtract b divided by 2a. So holy hell. I apologize for going through that, but like no one else is going to do that, every video except me. So, at least you get to see it in its scratchiest form. And if you can keep up with it, cool. So, and this, I'll make a separate video, a short, that this is the quadratic equation. That's what I want to do. I wanted to get to here in under a minute, make a short, and be like, this is the quadratic equation. It's the same thing as that. That would be, like, I ain't solving for it. It's actually pretty simple. Well, it's not too simple. Actually, it's not. It's just like, well, how do you get from there to there? That's a separate video. You know what I mean? But this is cool because you have a totally... It's the same. What I like on this is it's a check on reality. Like maybe I messed up the quadratic equation over here, and then so I have a check to make sure this quadratic equation is correct. Okay, so what is our a term, and do we want to use that as a check? Probably not. Let's just go back to the quadratic. I apologize, but we'll just go back to the quadratic equation. So our a term is 1 over, man, this speed of, I guess I'll keep with it. It's the velocity of sound. That's our A term. Our B term is negative. Why am I making mistakes? Holy Toledo. So, yeah, obviously, my B term is this negative 60 divided by Vs plus 1. Holy Toledo, just tons of mistakes. But no, I'm patting myself on the back right now because there's plenty of times where I won't catch that at all and just be in a pickle. But no, so our B term is 60 divided by Vs plus 1. That's our B term. Our C term is 900. Cool. So let's do the quadratic. X is equal to... Alright, so we have x is equal to negative b plus or minus the square root of b squared minus 4ac, oh, that's going to trip me up, divided by 2a. So we have x is equal to negative b, oh, thank goodness, that negative goes away. Alright, and then plus or minus the square root, we're going to square it, so the negative for sure goes away. And we're going to have 60 divided by Vs plus 1 squared. Now this is just a constant. Like literally, this is just a number. This is just a number. Because we know that Vs is equal to 320 meters per second. Oh, I didn't write that very good. Okay, so now we're going to have minus 4ac. Cool, so we have 4 divided by Vs. And then c. 900. And the only check is that we have a negative 4 divided by AC. So if A or C is negative, you know what I mean, that turns this positive. But no, it's negative. And then we're going to divide all by 2A, which dividing by 2 over VS. Okay, so hell yeah. So this is a constant. And VS, again, VS is 320. So right now, we have something that we can put into our calculator and actually get an answer. And hopefully, we didn't make too many mistakes. So we have 60. I'm going to store this 320 stored as, I'm going to store that as U. So this speed of sound will be U. Okay, cool. So we have 60 divided by alpha u plus 1 plus, we'll do the plus 1 first, square root of 60, oh I don't, nah, I need the parentheses, divided by alpha u plus 1 squared minus, now I don't need a parenthesis here, check this out, 4 divided by alpha u times 900. Like right here, it's not dividing by u, it's not putting, when you do 4 and then divided by your calculator, it'll just divide the next number. Then the following value, it'll put it up top. You know what I mean? So that's just pretty cool. I guess I'll go to the beginning of this because we got to divide by 2a. So I got my parentheses. That's the only thing about this calculator I do not like. It doesn't have like, I wish it had a button to go to the home and then end, just like a keyboard. Alright, divided by 2, because right here you have to do parentheses, divided by 2 divided by alpha u, and that's what we're going to do. I don't want to make any mistakes. That's not a real answer, so we're going to turn this to a negative, and where are we making mistakes, man? You know what I mean? I figure we were just good to go. This is part of the place where you just start crying, and you're just like, holy Toledo, we just spent all that time going over the quadratic equation. And why don't we have a check on this? You know, if we throw in 1.5 times 26.75 for that, at least we have numbers we can throw in. Cool, that's going to be equal to that, divided by 3, 20, and that's going to give us a time of 3.35. So now let's see where we made our mistakes. Yeah, that's why my videos I think are pretty decent, because I'll make mistakes and then, you know, we can find them, and hopefully you see them before I do. Whew. Okay, so hell yeah. So we had that, and then we threw in TA is 30 minus TS, and that's true because TA plus TS is equal to 30. So we're going to have 1.5 times 30 minus TS squared divided by VS. Cool. And then shouldn't this squared be, well, let's do this. So 3.2, so 30 minus 3.25 squared. Cool. That's that. And then what's this? 900 plus 3.25 squared minus 60 times 3.25. Okay, that's the same answer. Yeah, sweet. So we have a check on reality there. Oh, the 900. Look at that. So I found my error. I didn't divide 900 by VS. See how I was I foiled that through? Damn it, I don't like that one. Yeah. So cool. This 900 is divided by VS, and that's it. So that was amazing. You know what I mean? Because I'm getting better at finding errors, especially making videos. There's nothing crazier than making math videos. I just have a personality for it. I guarantee no one else would want to do that. So now when, and maybe that wasn't my error and I'm just bragging. But yeah, that 900 has to divide by VS. So we have 4. Now I am going to put parentheses here because I don't want to make a mistake. So we have 4 divided by U, and then we have 900 divided by U. Cool. Heck yeah. Oh, but bummer, man. Like, so that's one time value. And let's see if we do the positive, if it actually gives us a different time value. Okay, so that time value is totally wrong. Oh, and why? I feel like there's an error here because it's giving me a time for that speed of sound. That's going to be 2.38. But we already know it's getting hella high. So, yeah, I'm kind of bummed that we might have made like another mistake. Yeah, because, okay, let's do a check on reality. Because if we're saying that this now stored as alpha t, Yeah, okay, in past videos, like red flags are just going off that's not the answer, because I thought we did this, you know, using our numbers, and we got like 3.25 seconds. So now what they're saying is 30 minus alpha t. We're going to store that as alpha s. But no, they might be right. They might be right. So let's do the check on reality. So we're going to have 1.5. I have this stored as alpha s squared, and then we'll just square it. Divide by 320. No, because that's the time for the sound to get to us. Yep. Okay, so I'm gonna find my error, but I think we're close. Alright, hell yeah. So we're back, and I caught all my mistakes, and it's just nice to grab a fresh, clean sheet of paper, and we'll get to the mistakes that we made in a second, and we can get to just an easier way to get there. But this is the problem, you know, and just very simple. We have the acceleration on the way up, and so, cool, we have our velocity equation. We integrate, we get 3t. I'm just calling it t, not ta. And then I'm calling this equation t prime. I'm doing that because these are the equations. Okay, so and then when we integrate, we get position is 1.5 t squared. Cool. But now I can evaluate this equation at ta, so I know that. And then we have after the engine shuts off, it's just going to be like a stone going up and then coming down. And so we have gravity as our acceleration. Here's our equation. Velocity is negative 10 t prime, but we have an initial velocity. And the initial velocity is this velocity evaluated at ta. See how much crispier that looks? You know what I mean? Now when I have ta, and I even put ta in parentheses, just showing you that that's a constant. You know what I mean? It's not another variable. That's the value of ta that we're putting into that equation. Cool, that's the velocity. When we integrate again, we get you know, negative 5, because it's t squared. So yeah, we get negative 5t squared plus this term with a t. And ooh, oh, that's what I had. I had the prime. See, doing prime suck because I don't know how I would do that. But yeah, I want to call this t prime squared. That's a little ugly. But yep. That's why I made my mistake there. So I guess I don't like using primes either. But we'll figure out another symbol to use. Okay, so now we're going to take that velocity term times t prime, and then we have to have our initial position. Or our initial position for this equation is when we're hella high at time that time when the engine shuts off. That's like that 26, you know, so seconds. Cool. Cool, and then here's our continuity, and then I guess the only other one that I didn't have is like, well, once we get up to this height, we need to find what is time for the speed of sound to actually get to us. Once we're hella high, we're going to take that height, divide it by 320 meters per second. So that height is going to be 1.5 ta squared, this equation evaluated at that time, divided by velocity, speed of sound. Okay, hell yeah. And I can even just use this sheet of paper instead of, you know, because I can go through it. Right here, well, why would I throw in TS into there and square something stupid? You know what I mean? Let's solve this for TS. We'll do that right now. So TS is 30 minus TA. And I guess I can keep these just to you know, show what they are. So now I'm gonna throw this for TS right into there. So that value right into there. Cool. So now I'm gonna have 30 minus TA is equal to 1.5 TA squared divided by VS. So the quadratic equation on this is just going to be hella more simple. I'm going to have 1.5 VS. I'm going to put that in parentheses because this is going to be my A value for the quadratic. I'm going to have TA squared. I'm going to add, and then I'm even going to put a 1 out here, and then TA, because here's my B value for my quadratic, and then I'm going to subtract 30. Or I could even do this. I could even add negative 30, and then this really spells out that negative 30 is my C value for the quadratic. quadratic is negative b plus or minus the square root of b squared minus 4ac divided by 2a. Heck yeah. Now if I didn't run into mistakes, yeah, we might be using that other form of the quadratic to have a check on reality, but it's like, not no more. The second you start making mistakes, you're just like, you question life and you just want to get the answers. So we got negative 1, because our b value is 1, so negative 1 plus the square root. We're going to have 1 squared, so it's going to be 1 minus. Now here, hey, we have minus 4ac. So this is where I say, what's my a and c term? We have a negative for c and then we don't have a negative on a. So now we're just going to go plus, it's going to make it plus 4 times 1.5 divided by 320. And then the c value is negative. Oh, well, we already did that. Yeah, so I hate negatives. You know what I mean? I should have just done negative 4, parentheses 1.5 divided by 320, and then negative 30. But I didn't. I chose to just get rid of all the negatives. But man, I almost made an error there. Okay, so we're going to divide by 2a, and we're going to get the actual time, and I'll show you the error that we ran into when we set up the quadratic to try to find t. Right here, we're going to find ta. I set up the quadratic to find ts just because that's what I was most interested in. But that wasn't the easier quadratic to set up. Okay, we got to divide by 2a, which is, I'm just going to say it's 3 divided by 320. Cool. And check it out. We have a pretty damn good check on reality. TA is 26.66, repeat. And I thought it was 26.75. You know what I mean? So that was pretty cool. When I did the problem, I guessed 26.5 is a low end, 26.75 is a high end. But now we can throw it into this equation to get what TS is. So that's just going to be 30 minus that answer, and we get 3.33 repeat seconds. So cool, you know what I mean? Now where did I go wrong if I do say that TA is 30 minus TS, and then I want to square 30 minus TS, so that's going to be 900 plus TS squared. Minus 60 TS. So where did I go wrong? Well, I went wrong because, and then I just said this was divided by VS. If you go back, I did not multiply by 1.5 whole, you know what I mean? So that was the huge error here. And so then when I went to go put this into one of the equations, because what equation were we putting it into? We were putting it into this equation. So we were going to say that TS is equal to 1.5 divided by VS, and then this, 900 plus TS squared minus 60, TS. Cool, so that's what we had. And then so our quadratic, such a bugger right here. Can I do this kind of all in one step? We're going to have TS squared. Then we're going to have, I'm just going to do, no. Yeah, we got to do this right. So we have 1.5 divided by VS, and then we have TS squared. Then we have, I'm just going to say, what will we do? Plus or minus? Yeah, I'm just going to go minus 1.5 VS, and then we have parentheses. We have negative. Oh yeah. Oh, this is just tragic. It's hurting my mind right now. Let's just do this in a million steps, just so we don't make mistakes. So we have that plus 1.5 VS. We have that, and then minus 1.5 VS 60 TS. Cool. Let's now subtract this negative TS So now we could factor this. It just looks bizarre. So we're going to have negative and then 1.5 vs 60 minus 1. Cool. I mean plus 1. Yeah, I already just folded it through. So, and then the TS. Damn it. Yeah. It's so tragic when you just want to, like, you know, just get on with life. Let's throw some more time on the clock. Yeah, it makes math painful where you're just like, oh, bummer. I'm just going to make a mistake every step of the way. Let's get this as the constant over here. 1.5 vs times 900. Okay, cool. That's our constant. And then we'll have out front 1.5 vs ts squared. Hell yeah. And that's going to equal 0. So here's the A term. Here's the B term. And then here is the standalone C term. So we're going to have positive 1.5 vs 60 plus 1. Alright, and then plus the square root. We're going to have this squared. 1.5 vs times 60 plus 1 squared minus 4ac minus 4. The A and C terms aren't negative, so we will have that negative. So we minus 4, 1.5 vs, and then the C term, 1.5 vs times 900. Cool. Hell yeah. And then that's all divided by 2a. And this, I'm just going to go 3 divided by vs. Cool. So let's throw that into our calculator. It was just a little bit, you know what I mean? Yeah, that's too much. 1.5 divided by 320. Oh, let's use alpha u. Is alpha u still 320? Yes. 1.5 divided by alpha u times 60 plus 1. And then plus the square root. 1.5 divided by alpha u times just 60 is good enough. Plus 1 squared minus 4. 1.5 divided by alpha u. And then 1.5 divided by alpha u. Yeah, that's cool how that term comes up twice, you know what I mean? It's just fascinating to see those patterns in equations. Cool. And then divided by 3 divided by alpha u. Oh, hell no. Come on. Yeah, this is super bummer. I can't. Oh, whoa. You know what I mean? Is there like a negative somewhere that, you know, it should be a minus? You know, where you can't have a negative or something? Oh, yeah. Forget this, man. Forget this. Okay, I'm going to do it one more time because I want to find my error. You know what I mean? Because I thought like right here, because I'll show you where my error was. My error was right here. So it's just good to spot your error. So when I did 1.5 TA squared, I threw this in, and then we went through this, and then I just divided it by VS when we had to multiply by 1.5, and then find this quadratic. So the other way to just like forget the quadratic equation. Once you get here, if you think this is a check on reality, you can throw it into your calculator. Just bring this to the other side, and now we're going to go 1.5 divided by alpha u. I mean, it's just so nice to have other checks where you don't lose your mind. And this is our x term, x squared, minus 60x. Cool, minus x. And now we can graph it, and this should zoom 6. It should go through 3.3 or whatever. So I hate the quadratic. I swear, like I'll make a mistake every time. I don't like the negatives, and I think that psychs me out. I probably put all the negatives in the wrong location. Yeah, 3.3. So why, for the love, why can't I go from here? Why can't I go from here to the quadratic? You know, should I use my equation for the quadratic? I mean, we spent so much time deriving it. Look at that. I even put it in fluffy letters. So we're gonna use my equation. negative c divided by a plus b divided by 2a. It might not be friendly, but it should work. So why can't I get? I think it's factoring this. It messes with me, and I don't know why. So you know what I'm gonna do? If you need to solve a problem a different way, try to solve it in a very unique way. So what I'm gonna do, I'm gonna bring the TS this downstairs and bring all this constants to the other side. So if I have 1.5 over VS on this side, to get it to the other side, I have to divide it by, which is the same thing as putting it over here as VS 1.5. Cool, so let's do that. So that's going to be over there, and then I'm going to bring this TS down to this side, and now I have 900 to the TS to the negative 1 plus TS minus 60. You know what I mean? See what I did right there? And now from here, this is what I can do. I don't want a negative TS, so then I'm going to multiply everything by TS on this side and TS on this side. This is such a cool way to do it, because now I'm going to get that 900 alone plus TS squared, and then minus 60 TS. And now I have that equal to VS 1.5 TS. And for whatever reason, now these things just look just a little bit more appetizing to me. I mean, they're the same terms. So let's get this TS squared out in front. Oh, but you know what? Now I don't have any. The only thing that has that VS divided by 1.5 is right there. So that was just really useful. Instead of foiling all that crap through, like, we really clean this up. So now we have TS squared, and now we're gonna say I guess I'm gonna still do plus, and we're gonna have 60. Oh, bummer. We're gonna have I'm gonna do two steps at once. I need to get this over here, so that's just gonna be negative 60 TS minus VS 1.5 TS, and now I hate negatives. Look at that. So I'm just going to, well, I should just keep the negatives if I hate them so much. You know what I mean? Embrace them. And so that's what that's going to be. Might as well just keep it like that. TS squared plus negative 60 minus VS 1.5 TS plus 900 is equal to 0. Hell yeah. And yeah, we could try our equation. So we're going to have plus or minus the square root negative 900 divided by negative just 1 plus b. B is that. Negative 60 minus VS divided by 1.5 divided by 2a. That's just 2. We're squaring that entire thing. So this could be just this top squared divided by 4. You know what I mean? But now we're subtracting this b term. Yeah, it gets a little bit unruly. 1.5, but it's a check. It's another check on reality. And then we're going to divide that by 2a, which is just divided by 2. So sweet. Well, let's not mess this up. So we have the square root of negative 900 plus. See, it's not too bad. I'm just going to do this top part, negative 60 minus alpha u divided by 1.5. I'm going to square it and then just divide by 4, because I can see that. Okay, and now done with this square root thing. Now we're going to subtract. Yeah, and it is subtract b, so it's subtract negative 60 minus alpha u divided by 1.5. And we're going to divide by 2. And that's the positive root, so we're going to do the negative root and get the right answer. And heck yeah, booyah! So we get time s is equal to 3.33. Holy Toledo. That's the hardest part about this problem. And I'm so glad I ended on like using my form of the quadratic, and you know what I mean? I'm cursed. That quadratic equation, I'm cursed. Cool. But yeah, what was I going to say? Yeah, when you make mistakes, you've just created like a brand new problem of like, hey, find your error. And it's kind of fun, kind of not. Okay, so now we are, we're going to try to put everything together and try to get just like a full equation that can solve this problem. All right, hell yeah. So final push. And the cool thing about this is we can just get one equation, but we have this quadratic, and so we're going to go back to this continuity that was, you know what I mean, the time for the speed of sound to reach us was going to be that height. That's going to be that first equation evaluated at the time acceleration, you know what I mean, when the engine shuts off, divided by the speed of sound. And then when we throw in TS is equal to 30 minus TA, then we get this, and then when we solve it, here's our quadratic, where our A term is 1.5 VS, our B term is 1, and our C term is negative 30. You know what I mean? So now, and even this 30, we can recognize that's this T. I don't know what that acronym right there. You know what I mean? Let's just say T final, TF. So now we can get an equation with straight letters, so we can say that, and what are we solving for? We're solving for TA. So we can say TA is negative B, and in this case that's just negative 1, plus or minus, and there's nothing special about that, you know what I mean, because it's just a total constant, plus or minus divided by B squared, nothing special about that, plus 4. This 1.5, where the hell does this 1.5 come from? Well, that's going to be that initial acceleration. I'm going to call this acceleration A and then this G, the gravity. So now we have 4 divided by, this is going to be A divided by 2, the velocity of sound. And I wish I knew what kind of constants or label. I don't like this VS, but whatever. I've mentioned that before. And here's time final. Cool, and then divided by 2a and 2a is just, oh, yeah, and then again 2a. Cool. This is going to be that acceleration divided by 2svs, and don't get confused about the a as in acceleration. This is the a as in the quadratic constant. And so we're going to have 2 of these. So now that constant is going to be the acceleration of gravity. That acceleration is going to be 3 from the original problem. And that's going to be divided by Vs. So whew, if you could follow that, this is A divided by Vs. But now we have, and now let's do a quick check just to make sure. We got negative 1. Because I think it's the positive root for this one. But I don't know. I don't think there's a rhyme and reason. Of whether it's going to turn out positive or negative. Because when I do my quadratic equation in the funky way, it definitely, I think the root is different. Like the root, like we found out that it was the negative root. And this one I think is the positive root. So 3 divided by 2 divided by alpha u, and then time final of 30, all divided by 3 divided by u. Cool, heck yeah, and so that was the positive root. So now we're kind of good to go, and just going back to our original equations. And I'm sorry this page got so beat up, but yeah, right here. Here was our velocity and position going up, and then this was for the speed of sound, that 3 seconds. And what we wanted to know was after, yeah, this is. I just saw this TA, but I'm glad I put this because that's just the constant, you know what I mean? So that value is going to be that 26.66 seconds, but we're going to evaluate this equation at TS, and we just saw for TS is 3.3 repeat. So the answer to this problem is going to be velocity is equal to negative 10, or I guess velocity is equal to gravity, you know, acceleration of gravity, and it has to be negative, you know what I mean? So I might put a little caveat there, that negative. Maybe not. And then TS plus 3 TA. And we just found that TA is this, and from continuity, TS plus TA is equal to 30, so we can find TS. TS is just 30 minus TA. It's just 30 minus that. So cool. I mean, our equation gets a little bit big, but this is our final equation. We have velocity is equal to, okay, so it's equal to gravity. TS is going to be time final minus, and you know what I mean? Do we simplify this, or I mean it's I don't know. Not right now. It's time final minus TA. So we're gonna say minus, and I'm just gonna put that whole thing in brackets. -1 plus the square root of 1 plus 4. And even here I can simplify the 4 and just say it's 2. So yeah, let's do that. So 2a time final divided by speed of sound, and then all divided by acceleration divided by the speed of sound. Cool. Alright, so there is, that's what, did I just already make my first, no, yeah, 30 minus that, yeah, we're just saying 30 is time final. Cool. So there's that part of the equation, plus 3 times TA. Cool, so now we're going to go 3 times, and then just that thing again. And, we might be able to simplify this, but who cares? What I like to do is at least get it to here with letters, and then at least solve it once, you know what I mean, just to make sure, even though this is big. So we're going to go -10 stored as alpha G, so we got that. And even right now, I'm just going to go 30 stored as alpha T, because that's going to be that. Alpha U is this speed of sound. 3 stored as alpha A. And cool, and now we got this all in terms of letters. We're going to do this first part. We're going to go alpha G, square root, alpha T minus parentheses, another parentheses, -1, plus the square root, 1 plus 2 alpha A, alpha T divided by alpha U, done with the square root, done with the first set of parentheses, divided by another set of parentheses, alpha A divided by alpha U. Alright, and let's close this up. So I need 2 parentheses to close this up. Cool, that's closed. Plus 3 parentheses, another parentheses up top, -1, plus the square root, 1 plus 2 alpha A, alpha T, divided by alpha U. Cool. And then another parentheses. Right now I'm going to divide it by alpha A divided by alpha U. Close the parentheses. We're done. Hell yeah! And we get our velocity of 46.66. And we haven't even solved it, you know what I mean, with the values that we solved it with. But I'm sure that's the case, because didn't we say 3 plus 1 divided by 3 is 3 1/3 times 10. That's that. Plus 3 times 26 point, bunch of 6s. Oh, what? TA is 26.6 times 3 plus, whoa. Why did I get this velocity? Why did I get this equation right, but now it's like totally wrong? What the hell? Oh, it's -10. There you go. So -10 times 3.3s, bunch of 3s. And then we have plus 3 times 26.6, bunch of 6s. You know what I mean? Just make it really accurate. What the hell? So negative 10 times 3.3 plus 3 times 26.6. Cool, heck yeah. And you get 46.6 repeat meters per second. Man, that was brutal. So it's just fascinating. I probably will go, I'll probably make a really short version at the beginning of this video, but now you see how, like, yeah, if you're trying to get an equation with letters, yeah, it's very difficult, you know, it's difficult for me because you kind of lose touch of what's going on in letter form. But if you just throw numbers at it, it's kind of easy to see what's going on, a lot easier. So I'm going to see if I can clean this equation up. If I can't, I'm done with the video. But definitely at the beginning, I'm going to kind of go over this process, probably so the video just, at least people won't have to watch the whole darn thing to see how to get here. Alright, so sweet. Thanks for joining me, and that's a video.